Hi, welcome to Sunil Maths tutorial, functional analysis class number 41. In this video, we prove a theorem. Let us see the statement. If set EI is an orthonormal set in a Hilbert space capital H, and if X is an arbitrary vector in H, then X minus summation inner product of x comma xi into ei is perpendicular to ej for each j where summation runs over i remember that. So we prove this theorem. Let us take set ei is an orthonormal set. It is an orthonormal set. By the definition of orthonormal set in the Hilbert space capital H. By the definition of orthonormal set, in this set every vector is a unit vector. Every vector is a unit vector, and every pair of distinct vectors are orthogonal. Every pair of distinct vectors are orthogonal for I not equals to j. So remember that. So orthonormal set. Now to prove our theorem, define a set capital S is equals to set of some elements ei satisfying those condition inner product of x comma ei not equals to 0. We define a set with elements from the given set of all elements ei satisfying this condition inner product of x comma ei not equals to 0. Then, by the definition of this capital S, there may be two possibilities. Capital S is either empty, or capital S is countable. By this definition of S, there may be two possibilities. One is either the set S is empty set, it means it has no elements, and the set may be countable. Now let us see what happens. Case 1, S is empty. Let capital S is empty. If the set is empty, then obviously what it means, by the definition of the set, the inner product of x comma ei not equals to 0. If the set is empty, then the inner product of ei must be 0. For all I, the inner product of x comma ei is equals to 0. So this shows us summation inner product of x comma ei into ei is also 0 into ei, you get 0. It means x minus summation over I inner product of x comma ei into ei is equals to x minus 0. It is equals to simply x. Now you calculate the inner product further. Inner product of x minus summation over I inner product of x comma ei into ei comma ej is equals to inner product of x comma ej, because this term is completely 0. So you simply get again 0 because of inner product of x comma ei is equals to 0 for all I. So in this case, if this inner product is 0, then obviously you conclude that x minus summation over I inner product of x comma ei into ei is perpendicular to ej, because here this inner product is 0. So ej is perpendicular to this vector. So whenever the set S is empty, our theorem is completely proved. So we have to show that the same thing. Here you observe the statement x minus inner product of x minus summation over I inner product of x comma ei into ei is perpendicular to ej. So whenever the set S is empty, we prove the same thing. So our theorem is proved whenever S is empty. Now we go for case 2. Let us take, we said that S may be empty or S is countable. It means here the set capital S is countable. Let capital S is countable. S is countable means again there may be two possibilities. Capital S is finite or countably infinite or countably infinite. S may be finite or S may be countably infinite. Again, you have to two conditions. So here the set capital S is countable means we have two possibilities. One is either it is finite or countably infinite. So again we prove both the cases. Suppose S is finite. Suppose capital S is finite. Finite means it consists only limited number of elements. So let us take S is equals to E1, comma, E2, comma, and so on, En, having small n number of elements. Now define inner product of x comma ei into ei is nothing but summation over I is equals to 1 to n inner product of x comma ei into ei. So let us calculate the inner product x minus summation over I is equals to 1 to n inner product of x comma ei into ei comma ej is equals to inner product of x comma ej minus inner product of summation over I is equals to 1 to n x comma ei into ei comma ej. Again it can be written as inner product of x comma ej minus, write the summation outside of the inner product, summation over I is equals to 1 to n inner product of x comma ei into inner product of ei comma ej. Because our set is orthonormal set, so this can becomes x comma ej minus this summation becomes 1 only, so inner product of x comma ej, inner product of x comma ej. So because this term becomes either 1 or 0, either 1 or 0. So we get only at the place of x comma ej this summation, and this summation completely vanishes except this element inner product of x comma ej. So finally you get 0. So here you get inner product of x minus summation over I is equals to 1 to n x comma ei into ei comma ej is equals to 0. So it means x minus summation over I is equals to 1 to n inner product of x comma ei into ei is perpendicular to ej. This is the required condition. So whenever S is finite, our theorem is proved. Whenever S is finite, our theorem is proved. Now we assume that, or we state that S is countably infinite. Suppose capital S is countably infinite. If capital S is countably infinite, let the vectors of S be arranged in a sequence of order. Let the vectors of S be arranged. Let the vectors of S be arranged in a sequence of order. Say S is equals to E1, comma, E2, comma, and so on, EI, comma, and so on, EN, comma, and so on. Let the partial sum of S is Sn is equals to summation over I is equals to 1 to n inner product of x comma ei into ei. Here you have to remember this definition. We define the partial sum. Here S is countably infinite. And the elements of S can be arranged in this sequence, E1, E2, E3 and so on, En and so on up to infinity. We define the partial sum of S as Sn is equals to summation over I is equals to 1 to n inner product of x comma ei into ei. Now take for any integer small m greater than n, norm Sm minus Sn whole square is equals to norm summation over I is equals to 1 to m inner product of x comma ei into ei minus summation over I is equals to 1 to n inner product of x comma ei into ei whole square. It can be written as, because m greater than n, it can be written as norm summation over I is equals to n plus 1 to m inner product of x comma ei into ei whole square. So it can be written as inner product of summation over I is equals to n plus 1 to m inner product of x comma ei into ei comma summation over I is equals to 1 to m inner product of x comma ei into ei. So again this can be written as summation over I is equals to 1 to m inner product of x comma ei into inner product of ei comma summation over I is equals to 1 to m inner product of x comma ei into ei. Again it can be written as summation over I is equals to 1 to m inner product of x comma ei into summation over I is equals to 1 to, not 1, I'm sorry, this is n plus 1 everywhere, n plus 1 to m, n plus 1 to m inner product of x comma ei into ei comma ei. Here it is bar because we write from second element. For example, you observe that inner product of x comma beta x is equals to beta bar of inner product of x comma x. So similarly here in place of beta we have this term. So again it can be written as summation over I is equals to n plus 1 to m inner product of x comma ei into x comma ei bar, because summation runs over same elements, and this inner product of ei comma ei is equals to 1, no need to write that term. So which is equals to summation over I is equals to 1 to n plus 1 to m inner product of x comma ei. We know that z into z bar is equals to mod z square. By applying that property here, you get square. So right, now apply the Bessel's inequality. We know that, but Bessel's inequality, in the next video we prove the Bessel's inequality. In the but Bessel's inequality shows that summation over I is equals to 1 to n mod x comma inner product of x comma ei whole square converges. If it is converges by applying the Bessel's inequality, summation over I is equals to n plus 1 to m mod inner product of x comma ei whole square converges to 0. It means norm Sm minus Sn converges to 0 for large values of m comma n. This condition shows us norm Sm minus Sn converges to 0 means what it means. It means the sequence Sn is a Cauchy sequence. The sequence Sn is a Cauchy sequence in capital H. If the sequence Sn is a Cauchy sequence in capital H and H is a Hilbert space, every Hilbert space is complete. So the sequence, this shows us the sequence Sn is a convergent sequence, in capital H. If the sequence Sn convergent sequence in capital X, it means there exists a vector S in capital H such that Sn converges to S as n tends to infinity. It means limit n tends to infinity, Sn is equals to S. So now we write it the form. We write it as S is equals to summation over n is equals to 1 to infinity x comma en into en, because S is the limit for the sequence Sn. Now we define summation inner product of x comma ei into ei is equals to summation n is equals to 1 to infinity inner product of x comma en into en. In this final stage of this proof, right? In the final stage, the final stage of this proof, the final stage of this proof, we shall show that, we shall show that, we shall show that this sum is well defined. This sum is well defined. What we define here is well defined. That is what it means. It does not depends. It does not depends on the arrangement, on the arrangement of the vectors, of the vectors in capital S. It does not depend on the arrangement of the vectors in capital S. So right, remember this fact. Here you have to show that this sum is well defined. It means it does not depends on the arrangement of the vectors in capital X. Now we observe that. Now we observe that. Now we observe that inner product of x minus summation inner product of x comma ei into ei comma ej is equals to is simply x minus s comma ej. It can be written as, because this term is equivalent to s, it can be written as x comma ej minus s comma ej. It can be written as x inner product of x comma ej minus s can be written as limit n tends to infinity sn comma ej. It can be written as inner product of x comma ej minus limit sn comma ej, limit sn comma ej, by the continuity of inner product, by the continuity of inner product. Please remember here, I write here, by the continuity of inner product definition, by the continuity of inner product, if ej does not belongs to s, then inner product of sn comma ej is equals to summation over I is equals to 1 to n, summation over I is equals to 1 to n x comma ei into ei comma ej, which is equals to 0. What it means? Limit n tends to infinity inner product of sn comma ej is equals to 0. Limit n tends to infinity inner product of sn comma ej is equals to 0. So applying the same concept here, this term becomes completely 0. If that term completely becomes 0, x comma this completely 0, you get only x comma ej, only x comma ej. Again we go for s, we go for this. Already we learned that this inner product of x comma ej is equals to 0. So completely we get 0, we get 0 whenever so this element ej does not belongs to capital S, our complete calculation of this term becomes 0. X minus in summation x comma ei into ei comma ej must becomes 0. After this, what happens if ej belongs to S? If ej belongs to S, if ej belongs to S, if ej belongs to S, then Sn comma ej can be written as Sn comma ej can be written as in summation inner product summation 1 to n x comma ei into ei comma ej. It can be written as this term is nothing but x comma ej. If n greater than j, here also if n greater than j. So then our condition becomes inner product of x minus summation over I is equals to 1 to n x comma ei into ei comma ej is equals to x comma ej minus x comma ej. So what you get? Again 0. In both the cases, in both the cases, whether ej belongs to s or ej does not belongs to s, in both the cases, inner product of x minus summation inner product of x comma ei into ei comma ej is equals to 0. It means the element x minus summation x comma ei into ei is perpendicular to ej for every or for each j. For each j. So our main condition is fulfilled. We have to show that this condition only. So this is proved. And finally, we shall conclude the proof. We shall conclude the proof. We shall conclude the proof by showing that our definition of summation inner product of x comma ei into ei is valid. We prove that the required condition, the element is perpendicular to ej, but our definition of this inner product summation x comma ei into ei is valid. We have to show that. So finally, to prove this, let the vectors of s be arranged in any manner. In the previous case, the elements of s can be arranged in order, but here there is no particular order. You can arrange it in any manner. That is, s can be written like this: f1 comma f2 comma and so on, fn comma and so on. We put the partial sum Sn dash is equals to summation over I is equals to 1 to n inner product of x comma e inner product of x comma, now we use fi, inner product of x comma fi into fi. As shown above, the sequence Sn dash, will converge. The sequence Sn dash will converge to a vector s dash in capital H. Then we write s dash is equals to summation over n is equals to 1 to infinity inner product of x comma fn into fn. Our aim is to show that s is equals to s dash. So let us take epsilon greater than 0. And let n naught be a positive integer. Such that small n greater than or equals to n naught. Then obviously we have norm Sn minus s is less than epsilon, as well as norm Sn dash minus s dash is also less than epsilon. So summation over I is equals to n naught plus 1 to infinity mod x comma ei whole square is less than epsilon square. For some positive integer, again, for some positive integer m naught greater than n naught, all terms of Sn naught occur among those Sm naught dash such that Sm naught dash minus Sn naught is finite sum consisting of terms, consisting of terms consisting of the terms of the type inner product of x comma ei into ei for I is equals to n naught plus 1 comma n naught plus 2 n naught plus 3 and so on. Now norm sm naught dash minus sn naught dash is less than or equals to summation over I is equals to n naught plus 1 to infinity mod inner product of x comma ei into ei whole square. So this is less than epsilon square. So what you get obviously norm sm naught dash minus sn naught dash is less than epsilon square, which is less than epsilon because epsilon is an arbitrary small number. Now consequently you can write like this: norm s dash minus s is equals to norm s dash minus sm naught dash plus sm naught dash minus sn naught plus sn naught minus s. Split the norm, which is less than or equals to norm s dash minus sm naught dash plus norm sm naught dash minus sn naught plus norm sn naught minus s. Every norm is less than epsilon. Epsilon plus epsilon plus epsilon, which is less than 3 epsilon. 3 epsilon. And epsilon is arbitrary. We choose it as small. We choose it as small as we need. As small as we need. So we conclude that norm s dash minus s is less than epsilon, but always norm s dash minus s less than epsilon, and if you choose it is 0, so s dash minus s is equals to 0. So obviously this condition implies s dash is equals to s. This completes the proof. Of our theorem. One of the lengthiest theorem in this chapter. So be patient to learn this theorem. Keep learning. In the next video, we learn the Bessel's inequality in the Hilbert spaces. Keep learning.